Hello, this is Yan again. Previously, we discussed that normal distribution is helpful in estimating probabilities, especially when we transform the normal distribution into a standard normal distribution and use the z-score to find the proportion of the area under the curve, which is also the probability. And in this chapter, we'll start with the probability again. In inferential statistics, we select a sample of data from a large population so that we can measure the mean and the variance in the small sample to gauge the mean and the variance in the population. Say we have a population of 100 women to sample from. The probability of any woman to be selected as the first subject is 1 out of 100, which is 0.01. And there are two ways that we can sample the second woman. The first method is to put the first woman back and sample the second time from the whole set of 100 women again. And the probability of any woman to be selected as the second subject is still 1 out of 100, which is still 0.01. And that's sampling with replacement, in which each participant selected is replaced before the next selection. And the second method is to keep the first woman out and sample the second time from the remaining 99 women. The probability of any of the rest of the women to be selected as the second subject is 1 out of 99, which is 0.010101. And that's sampling without replacement, in which each participant selected is not replaced before the next selection. In sampling with replacement, for each selection, the probability will be the same, 0.01. But in sampling without replacement, for the first selection, the probability is 0.01. And the second selection is 0.010101, which is actually a little bit larger than the first probability. And for the third time, you can imagine the denominator will be 100 minus 2, which is 98. So the probability will increase a bit more. So the probability of each selection will change because the denominator will get smaller and smaller while we keep taking out subjects without replacing them. When the probabilities are not the same but conditional, it is called a conditional probability. In our example, the sampling order was not an issue, but there are times when the order matters. For instance, we have a small population of 3 subjects, and we want to take a sample of 2 out of the population of 3. When the order doesn't matter, A first and B second, or B first and A second are considered the same sample. But when the order matters, A first, B second, and B first, A second are 2 different samples. In theoretical sampling, the order of selecting individuals matter, and each individual selected is replaced before sampling again. In experimental sampling, the order of selecting individuals does not matter, and each individual selected is not replaced before selecting again. So, using the same example, we take a sample of 2 out of a population of 3. So if we use the theoretical sampling strategy, the number of total possible samples is 9. And if we use the experimental sampling strategy, the total possible samples is 3. And here is the computation. If you have problems with the factorial operation and the combination formula, please view the videos that I attached to this week's learning modules. But how to compute the number of possible samples is not our priority. We introduced the sampling strategies because next step we'll learn about a sampling distribution, in which we'll use a theoretical sampling strategy to select samples from a population. What is a sampling distribution and how do we get there? First, we identify a population of interest, the red distribution. And then we randomly select a sample of size n, the lowercase n, using the theoretical sampling strategy. And then we select another one, and another one, until we get all the possible samples. And in this example, there are 4 samples, A, B, C, and D. For each sample, there is a sample mean. That's x bar A, x bar B, x bar C, x bar D. Those are the sample means. Using all the sample means as new scores, we create a sampling distribution, a distribution of sample means. We select the samples because we want to use the sample statistics to gauge population parameters. In the next few slides, we'll discuss how the sample mean is related to the population mean. We randomly select the sample means. Let's use the same example of the small population of 3 subjects. But this time we're going to give them a score. A is 8, B is 5, and C is 2. The population mean is 5. If we use the theoretical sampling strategy, so we sample with replacement and the order matters, and we sample 2 participants from the population of 3 each time, and we'll end up with 9 samples in total. And we calculate the sample means for each sample. If you look at some of the sample means, this one is 3.5 and this one is 2. They are not even close to the population mean 5. But continue with the same example. This is the frequency distribution of the population. It is a non-model because there is only one count for each score. Using the theoretical sampling strategy, we get 9 samples in total. If we distribute the 9 sample means, they are normally distributed. And this outcome is described by the central limit theorem. The central limit theorem explains that regardless of the scores in the distribution of scores in a population, the sampling distribution of a sample means selected at random from the population will approach the shape of a normal distribution as the number of samples in the sampling distribution increases. What this says is the original population is not normally distributed. Imagine you only have 4 samples. This one, and this one. Your distribution will look something like this. It's positively skewed. If you have 2 more samples, say this one, your distribution will look like this, and it's more symmetrical now. And if you have 3 more samples, your sampling distribution will look something like this. And it's close to normal distribution. So the more samples you have, the closer your sampling distribution is to the normal distribution. And one important implication of the central limit theorem is the probability of obtaining a sample mean from a population is normally distributed. And that means 90% of all the possible sample means will fall within 2 standard deviation of the population mean. And by now you probably have already memorized the 3 numbers 68, 95, and 99.7. And this graph is from chapter 4, the empirical rule. The standard deviation of a sampling distribution is called a standard error of the mean, or standard error. It is represented by sigma with a subscript uppercase M. The uppercase M means the mean of each sample. Mu with a subscript uppercase M represents the mean of the sampling distribution, which equals the population mean. N to the nth power is the total number of possible samples. So when we use the notation for sampling distribution, the formula of standard error of the mean looks like this. Here's the example from our textbook. The mean of the sampling distribution is 5, and total number of possible samples is 9. And then 9 sample means are listed here. So first we calculated the sum of sum of squares, which is 27, and then we get the standard error. It is 1.73. This is the shortcut formula for standard error of the mean. The numerator is the standard deviation of the population, and the denominator is the squared sample size. Apparently, these are the 2 factors that affect the standard error of the mean. The numerator and the standard error of the mean are positively related, which means when one goes up, the other one goes up. When one goes down, the other one goes down. This you can tell from this graph. When the population standard deviation goes up, the standard error of the mean goes up. When the population standard deviation goes down, the standard error of the mean comes down. The denominator, the squared sample size, and the standard error, they are negatively related, which means when one goes up, the other one goes down. When the sample size gets bigger, the standard error gets smaller. When the sample size gets smaller, the standard error gets bigger. And this is also explained in the law of large numbers, which states increasing the number of observations or sample size will decrease the standard error of the mean. That means larger samples are associated with a smaller sampling error and closer estimates of the population mean on average. A sampling distribution can be converted to a standard normal distribution by applying the Z transformation, which is used to determine the likelihood of obtaining a particular sample mean from a population. And the way to calculate the z-score is the same. We get the deviation of a particular sample mean from the mean of the sampling distribution and divide it by the standard error of the mean. This is an example from our textbook, the example 6.4 on page 172. The mean of the sampling distribution is 151. Standard deviation of the population is 9. The sample size is 100. So the question is, what is the probability of obtaining a particular sample with a mean larger than 153? First, I like to draw a normal distribution and then mark the scores, which helps me to determine which portion under the curve that I'm looking for. So the mean is 151 and the particular sample mean is 153, and I'm looking for the probability of getting a score larger than 153. So I shadowed this right tail, and that's the proportion I need to find out. And then I calculated the standard error, which is 0.9, and I used the standard error to get the z-score, which is 2.22, and the z-score is corresponding to this 153. And the last step is I go to the unit normal table on page 479 at the end of our textbook and find the proportion under the curve, and which is 0.0132, and that's the probability of obtaining a sample with a mean larger than 153.